Today we're going to take a look at how to measure the accuracy of a binary classification model. Let's take a look at an example. Let's suppose we're working for a music streaming service and are tasked with predicting whether a song would be a good recommendation. We think we're smart, so we build a logistic regression model. We set a threshold value of 0.5, and anything above this threshold value is considered to be a yes, indicating that this is a good song recommendation. Anything below this threshold value is supposed to be a no, indicating a bad song recommendation. To start off looking at the generic accuracy approach, we can use this formula, number of correct predictions over total predictions. Now we have to ask ourselves, what does it mean for our model to be correct? First, we can have a song recommendation our model provides actually be a good song. This is called a true positive. It was true for our positive case, where a song is good, hence our model is correct. Second, if the model predicts a song was good but it was actually bad, this is called a false positive, or type 1 error, hence our model is incorrect. If the model predicts that the song was bad and the song was actually bad, this is a true negative. The negative case, the song being bad, is true, hence our model is correct. Lastly, if the model tells us that the song was bad but it was actually good, this is known as a false negative, or type 2 error. Hence, our model is incorrect. We can now rewrite the accuracy formula in terms of these 4 different situations. We typically summarize these different metrics in something known as a confusion matrix. Here's an example of it filled out. Using the values of this confusion matrix, we can calculate the accuracy of our model. Here we see it's 86%. Now, accuracy doesn't always tell us the full picture. If our model makes a recommendation for a song, how sure are we that the song is actually good? For this, we try to measure how well our model prevents against type 1 errors or false positives. And to do that, we use precision. We basically take a look at the song recommendations our model made and see which portion of them were actually good. Using the same confusion matrix, we can see our model predicted 12 values as being good. And if we take a look at the formula, we can calculate the precision to be around 83%. So around 83% of the songs our model predicts are actually good song recommendations. Now, we may also have a different question, a question that relates to the false negatives, or in other words, how good is our model at finding all the good songs? To do this, we use recall, sensitivity, or true positive rate. They're all the same thing. Now we can see that there are actually 11 songs that were good, and our model was able to capture 10 out of 11 out of them. Hence, our recall value would be 91%. Sometimes we may want to assign a single value to the accuracy of our model to encompass both the precision and the recall. To do this, we use a measure known as F1 score. Now, the F1 score is a harmonic mean, which is a good way of finding the balance between 2 rates. This simplifies down to 2 times the precision times the recall over the precision plus the recall. We can calculate this using the prior values from the previous slides and see that our F1 score is 87%. Now, I wouldn't solely use the F1 score because it is a bit misleading sometimes, so make sure to always take a look at your precision and recall values. In creating the model, if you remembered, we use a specific threshold value to determine whether the output of our model is a yes or a no. That value was 0.5, but there are many threshold values we could have chosen. The confusion matrix we got was a result of using a specific threshold value. More often than not, we need a way to measure the accuracy of a model given different threshold values. For this, we use the Roc curve. The Roc curve compares a true positive rate with a false positive rate. We can point plots on this graph to evaluate the accuracy of models with different threshold values. A point at 1, 1 is the same as having a threshold value of 0, where we say everything is a good song recommendation. A point at 0, 0 is the same as having a threshold value of 1, where we say almost nothing is a good song recommendation. The diagonal line dotted across the ROC curve shows where our random model would lay. So we can evaluate if our model is doing better or not than just randomly choosing yes or no. The false positive rate tries to find our type 1 error and tells us how often we are to expect our good song recommendation to actually be bad. It simplifies down to false positives over false positives plus true negatives. Now, using the values in this confusion matrix, we can see that we have a false positive rate of around 19%. True positive rate, if you can recall, is just recall. So if you remember, our true positive rate for this confusion matrix was 91%. Given these two values, we're able to plot a point on the ROC curve for our given threshold value. Similarly, we can generate other points on this graph. And if we connect the lines between these points, we can get the ROC curve, where our threshold values will lay. If the model was hypothetically perfect, it would have a false positive rate of 0 and a true positive rate of 1, making the ideal model or the perfect model lay at 0, 1. So the closer your model is to the point of 0, 1, technically it should be better. You'll notice that the curve indicates a trade-off between having a low false positive rate and a high true positive rate. And indeed, this is true for many models. As the threshold value decreases from 0.5 to 0.3, we can see that we get more false positives and we get actually less false negatives, indicated by the increase in true positive rate. And as the threshold increases, we get less false positives and more false negatives. To determine what the optimal threshold value should be, we have to ask ourselves what we care about. In our case, we care more about giving a good song recommendation than getting all the songs that could possibly be correct. So we care more about false positives being low. Our optimal value would be a threshold value of 0.8. There may be other models where you care more about the false negatives. For example, for a model that measures cancer, you'd want a low false negative rate. Why? Because the consequences of missing a case where someone does have cancer are more severe than the consequences of falsely diagnosing someone with cancer. And one last thing I want to mention is that the ROC curve, although it be a good way to assess the accuracy of a model at different threshold values, it is not a good indicator in all situations of how well your model is actually doing. Specifically, the ROC curve is good for balanced data sets, where you have an equal representation of positive cases and negative cases. In situations where you have an unbalanced data set, I would go for a precision versus recall curve, which is the same thing as the ROC curve, except you're measuring precision versus recall.